In this video, we will see the examples based on groundwater hydrology. Let's see the first numerical. In an area of 22 km square, the water table dropped by 3 meter. If the porosity is 30% and the specific retention is 14%, determine the specific yield of the aquifer and the change in the groundwater storage. Here, the area of the aquifer is 22 km square. Kilometer square, and if I write it in meter square, then it will be 22 into 10 raised to 6 meter square. Next, water table dropped by 3 meter. So the drop in groundwater table is equal to 3 meter. The porosity is 30%. So porosity is equal to 30%, or say 0.3. And the specific retention is 14%. I'm writing it here. So SR is equal to 14%, that is 0.14. First we have to find the specific yield of the aquifer. We know that porosity is equal to specific yield plus specific retention. So SY will be equal to porosity minus specific retention, that is 0.3 minus 0.14. So the specific yield will be equal to 0.16. And if we want to write it in percentage, then it will be 16%. Next we have to find the change in groundwater storage. Change in groundwater storage is equal to area of aquifer into drop in groundwater table into specific yield. We have all the values, so I'll just put it in this equation. So change in water storage will be equal to area of aquifer, that is 22 into 10 raised to 6 meter square, into drop in groundwater table is 3 meter, and specific yield is 0.16. So the change in the groundwater storage is equal to 10.56 into 10 raised to 6 meter cube. So we have got the specific yield is 0.16 and the change in the groundwater storage comes out to be 10.56 into 10 raised to 6 meter cube. Let's see the second numerical. A field test for permeability consists in observing the time required for a tracer to travel between two observation wells. A tracer was found to take 10 hours to travel between two wells 50 meter apart when the difference in the water surface elevation in them was 0.5 meter. The mean particle size of the aquifer was 1 mm and the porosity of the medium is 0.3. If the kinematic viscosity is 0.01 cm square per second, estimate the coefficient of permeability, intrinsic permeability of the aquifer, and the Reynolds number of the flow. Here we have to find the coefficient of permeability, and we know that V is equal to Ki. So first of all, we'll have to find V, that is the discharge velocity. So to find the discharge velocity, first we need to find the actual velocity of water. And the actual velocity of water will be equal to the distance between the two wells divided by time taken by the tracer to travel between two wells. As you can see here that the distance between the two wells is 50 meter, as the two wells are 50 meter apart. So it will be 50 divided by, tracer was found to take 10 hours. So the time is 10 hours and we convert it in second. So 10 into 60 into 60. And here also we are converting 50 meter to centimeter. So we'll multiply it with 100. So the actual velocity is equal to 0.139 centimeter per second. Then we also know that the actual velocity is equal to discharge velocity divided by porosity. So the discharge velocity will be equal to actual velocity into porosity, and actual velocity is 0.139 centimeter per second into porosity is 30%. So 0.3. Hence the discharge velocity is equal to 0.0417 centimeter per second. Next, we know that the discharge velocity is equal to Ki. So to find the coefficient of permeability, we will need the hydraulic gradient, that is I. And I is equal to dH upon dL. Here, the difference in the water surface elevation is 0.5 meter. And we know that the wells are 50 meter apart. So the difference in the water surface elevation, that is dH, is 0.5 meter. So 0.5 divided by dl, that is 50. So this will be 10 raised to minus 2. Now we'll find out K. So K is equal to the discharge velocity divided by I. So K is equal to V upon I, and it will be equal to 0.0417 into 10 raised to minus 2 divided by 10 raised to minus 2. Here I have multiplied this 10 raised to minus 2 to convert it from centimeter per second to meter per second. So it will be equal to 0.0417 meter per second. So the coefficient of permeability is 0.0417 meter per second, or we can say 4.17 centimeter per second. Next we have to find the intrinsic permeability. So intrinsic permeability, that is K naught, is equal to K into nu divided by G. So K is 4.17 centimeter per second. Nu, that is kinematic viscosity given to us, is 0.01 centimeter square per second. Then G, as we know, it will be 9.81, but meter per second square. So we'll convert it in centimeter per second square. So multiplying it with 100. On solving, we get K naught is equal to 4.25 into 10 raised to minus 5 centimeter square. Let's convert this from centimeter square to Darcy. So we know that 9.87 into 10 raised to minus 9 centimeter square is equal to 1 Darcy. So K0 will be equal to 4.25 into 10 raised to minus 5 divided by 9.87 into 10 raised to minus 9. So it is equal to 4307 Darcy's. Next, we have to find the Reynolds number. See here, the mean particle size of the aquifer is 1 mm. Reynolds number is equal to VDA upon nu. So V is 0.0417, dA is 1, it is in mm, so I'll convert it in centimeter as we have written the discharge velocity in centimeter per second. So 1 into 10 raised to minus 1 divided by nu, that is kinematic viscosity is 0.01 centimeter square per second. So RE comes out to be 0.417. Numerical 3. An artesian aquifer 20 meter thick has a porosity of 20% and the bulk modulus of compression is 10 raised to 8 Newton per meter square. Bulk modulus of elasticity of water is 2.1 into 10 raised to 9 Newton per meter square. Estimate the storage coefficient of the aquifer. The thickness of the aquifer is 20 meter. That is B is equal to 20 meter. Porosity is 20%. So it will be equal to 0.2. Then bulk modulus of compression is 10 raised to 8 Newton per meter square. Bulk modulus of compression is ES and ES is equal to 10 raised to 8 Newton per meter square. Then the bulk modulus of elasticity of water is 2.1 into 10 raised to 9 Newton per meter square. So we denote the bulk modulus of elasticity of water as Kw and it is equal to 2.1 into 10 raised to 9 Newton per meter square. We have to find the storage coefficient of the aquifer. So we know that the equation for the storage coefficient of aquifer is S is equal to gamma W into B into alpha plus porosity into beta. First of all, we'll find alpha and beta. Alpha is equal to 1 upon ES and ES is 10 raised to 8 Newton per meter square. So alpha will be equal to 1 upon 10 raised to 8 Newton per meter square. Then beta is equal to 1 upon Kw. Kw is 2.1 into 10 raised to 9 Newton per meter square. So this will be 1 upon 2.1 into 10 raised to 9. Then we'll substitute all the values in this equation and find the storage coefficient. So gamma W is 9810 Newton per meter cube into B. So B is 20 meter. That is the thickness of the aquifer. Alpha, that is 1 upon 10 raised to 8, plus porosity is zero point 0.2 and beta is 1 upon 2.1 into 10 raised to 9. So on solving this, we get 1.98 into 10 raised to minus 3. So we can say it equal to 2 into 10 raised to minus 3. Therefore, the storage coefficient is 0.002. Let's see the next numerical. A tube well penetrates fully in an unconfined aquifer. Calculate the discharge from the tube well under the following conditions. Diameter of the well is 30 cm, drawdown is 3 meter, effective length of the strainer is 15 meter, coefficient of permeability of the aquifer is 0.05 cm per second, and the radius of zero drawdown is 300 meter. First of all, let's write down the data given to us. Here the aquifer is unconfined aquifer. The diameter of the well is 30 cm, which means the radius of the well is 15 cm. And if I write in meter, then it will be 0.15 meter. Drawdown is equal to 3 meter. So S is equal to 3 meter. Then the length of the strainer, effective length of the strainer is 15 meter. So L is equal to 15 meter. The coefficient of permeability, that is K, is given 0.05 centimeter per second. Next, the radius of zero drawdown is 300 meter. That is, capital R is equal to 300 meter. First, let's convert this centimeter per second to meter per second. So K will be equal to 0.05 centimeter per second is given to us. So it will be 0.05 into 10 raised to minus 2 meter per second. The equation for discharge is Q is equal to 2.72 Ks into L plus S by 2 divided by log capital R upon R to the base 10. We just need to put the values. So Q is equal to 2.72 into K. K is 0.05 into 10 raised to minus 2. S is 3. Then L is 15 plus S by 2. So it will be 3 by 2 divided by log capital R, it is 300 meter, divided by R, it is 0.15 meter, and to the base 10. So on solving this, we get Q is equal to 0.02039 meter cube per second, and in liters per second it will be 20.39 liter per second. Fifth numerical. Design a tube well for the following data. Yield required is 0.20 cumex. Radius of the circle of influence is 300 meter. Drawdown is 6 meter. Thickness of the confined aquifer is 40 meter. And permeability coefficient is 80 meter per day. Let's write the data given. Yield required is 0.20 cumex. So Q is equal to 0.20 meter cube per second. Radius of circle of influence, that is capital R, is equal to 300 meter. Then drawdown is 6 meter. So S is equal to 6 meter. Thickness of the confined aquifer. The thickness of the confined aquifer is 40 meter. So B is equal to 40 meter. Then the permeability coefficient is 80 meter per day. As the discharge is in meter cube per second, we'll convert this from meter per day to meter per second. So it will be 80 divided by 24 into 60 into 60. As one day is 24 hours, 60 minutes, 60 seconds. So on solving this, we get 9.26 into 10 raised to minus 4 meter per second. Here it is confined aquifer, and the equation for discharge is Q is equal to 2.72 kbs divided by log capital R upon R to the base 10. Then we just have to put the values, and what we'll find out the radius of the well. So here we have Q as 0.20 is equal to 2.72 into K. K is 9.26 into 10 raised to minus 4 into B. B is 40 meter. Drawdown is 6 meter divided by log capital R is 300 meter divided by R. Next what you will do is bring this log 300 upon R to the base 10 here and find out 2.72 into 9.26 into 10 raised to minus 4 into 40 into 6 divided by 0.2. On solving we get log 300 upon R to the base 10 is equal to 3.022464. Next, you have to find out the antilog. So 300 upon R is equal to antilog of 3.022464. And this is coming as 1053.08. So 300 upon R is equal to 1053.08. So R will be equal to 300 divided by 1053.08, and on solving this we get R is equal to 0.285 meter, that is 28.5 centimeter. So I am taking this equal to 29 centimeter, so that I get a round off value for the diameter of the well. And so the diameter of the well will be equal to 29 into 2, that is 58 centimeter. See, the question was to design a tube well. So whenever it is asked to design a tube well, then we need to find out the diameter of the well. Let's see the next numerical, numerical 6. A 30 centimeter well completely penetrates an unconfined aquifer of saturated depth 25 meter. After a long period of pumping at a steady rate of 2100 liters per minute, the drawdown in two observation wells, 30 meter and 90 meter, from the pumping well were found to be 5 meter and 4 meter respectively. Determine the transmissibility of the aquifer. What is the drawdown at the pumping well? First of all, let's write the data given to us. A 30 centimeter well. So the diameter of the well is 30 centimeter and the radius of the well will be 15 centimeter. Penetrates an unconfined aquifer of saturated depth 25 meter. So the thickness of the aquifer, which we denote it as capital H, is given as 25 meter. After a long period of pumping at a steady rate of 2100 liters per minute. So Q is equal to 2100 liters per minute. The drawdown in two observation wells, 30 meter and 90 meter, from the pumping well were found to be 5 meter and 4 meter respectively. So here the drawdown were found to be 5 meter and 4 meter respectively. So S1 is equal to 5 meter and S2 is equal to 4 meter. And the wells are at radial distance R1 equal to 30 meter and R2 is equal to 90 meter. First, let's convert this from liters per minute to meter cube per second. So Q is equal to 2100 liters per minute is given to us. So 2100 into 10 raised to minus 3, which we'll get in meter cube, and then dividing it by 60. So we'll get it in meter cube per second. And it is coming as 0.035 meter cube per second. Then for steady state flow to wells in unconfined aquifer, Q is equal to pi k H2 square minus H1 square divided by ln R2 by R1. First, we'll find out H2 and H1. H1 is equal to H minus S1 and H2 is equal to H minus S2. H is 25 meter, S1 is 5 meter, so this will be 20 meter. And here H is 25 meter, S2 is 4 meter, so H2 will be equal to 21 meter. Now we just have to put all these values in the equation. Q is 0.035 is equal to pi k H2 square. H2 is 21 21 square minus H1 is 20, so 20 square divided by ln R2. R2 is 90 meter and R1 is 30 meter. So ln 90 by 30. On solving this, we'll get the value of K, that is the coefficient of permeability. K is equal to 2.9852 into 10 raised to minus 4 meter per second. And if I want to find it in meter per day, then it will be just you have to multiply this value into 24 into 60 into 60, and on solving we'll get 25.8 meter per day. We have to find the transmissibility of the aquifer, and transmissibility is equal to K into H. So K is 2.9852 into 10 raised to minus 4 into H. H is 25. So we get 7.463 into 10 raised to minus 3 meter square per second. Same way, if you want to find this in meter square per day, then just multiply this value into 24 into 60 into 60, and on solving we are getting T is equal to 645 meter square per day. Next we have to find out the drawdown at the pumping well. So Q will be equal to pi K H1 square minus HW square divided by ln R1 upon RW. See, we have to find out the drawdown. So drawdown is given as SW is equal to H minus HW. I'll show you this by using a diagram. Here, as we can see, that at the well face, the drawdown is SW, and we need to find out SW. So what we will do, from this H we'll subtract HW. So SW is equal to H minus HW. In exam, while solving the sum, there is no need to draw the diagram. I have just shown you this for better understanding. Let's get back to the calculations. See here, we have Q, then the coefficient of permeability, H1, R1 and RW. All the values we are having. So from this equation, we'll get HW. Q is equal to 0.035 pi into K. K is 2.9852 into 10 raised to minus 4 and into H1 square, that is 20 square minus HW square, whole divided by ln R1 upon RW. R1 is 30 and we know that RW is 0.15. So on solving this equation, we'll get HW. HW is equal to 14.22 meter. See, HW is the depth of water in the well, which is measured above the impermeable strata. And then, as I told you, that the drawdown, which we denote it as SW, will be equal to H minus HW. So H is 25 meter minus HW is 14.22. So SW is equal to 10.78 meter. Seventh numerical. A well penetrates fully a 10 meter thick water bearing stratum of medium sand having coefficient of permeability of 0.004 meter per second. The well radius is 100 mm and is to be worked under a drawdown of 4 meter at the well face. Calculate the discharge from the well. What will be the percentage increase in the discharge if the radius of the well is doubled? Take R is equal to 300 meter in each case. Here, a well penetrates fully a 10 meter thick water bearing stratum. So it is the case of confined aquifer. Then the thickness of the aquifer is 10 meter. The coefficient of permeability is 0.004 meter per second. That is K is equal to 0.004 meter per second. The well radius is 100 mm. So R is equal to 100 mm. And if I write it in meter, then it will be 100 divided by 1000. So 0.1 meter. Drawdown is 4 meter. That is S is equal to 4 meter. Then we know that the equation for discharge for the confined aquifer is Q is equal to 2.72 into KBS divided by log capital R upon R to the base 10. We'll substitute all the values. So Q is equal to 2.72 into K. K is 0.004 into B is 10. S is 4 divided by log capital R is 300 and R is 0.1 to the base 10. So on solving this, we get Q is equal to 0.125 meter cube per second. So the discharge from the well is 0.125 meter cube per second. The next question is, what will be the percentage increase in the discharge if the radius of the well is doubled? So we know that the radius of the well is 100 mm. Now the radius of the well is doubled. That is, R will be equal to 200 mm. It is equal to 0.2 meter. Again we'll find out the discharge when R is 200 mm. So this is Q1 and now we are finding out Q2. Again using the equation, so 2.72 into K, that is 0.004 into B, that is 10 into S is 4 divided by log to the base 10 300 upon R, and now in this case R is 0.2 meter. On solving this, we get Q2 is equal to 0.137 meter cube per second. See, here in the question, it is asked to find the percentage increase in the discharge. So, the percentage increase in discharge is equal to Q2 minus Q1 upon Q1 into 100. So, Q2 is 0.137 minus Q1 is 0.125 and divided by 0.125. So, the percentage increase in discharge is equal to 9.6%. So, if the radius of the well is doubled, then the percentage increase in the discharge will be equal to 9.6%. Let's see the last numerical 8. In a recuperation test of a 3 meter diameter open well, the water table changed from 114.6 meter to 115.7 meter elevation in 120 minutes. If the water table elevation is 117 meter, determine the specific capacity per unit well area of the aquifer and the discharge in the well under a safe drawdown of 2.75 meter. Here, the diameter of the open well is 3 meter. That is D is equal to 3 meter. The water level changed from 114.6 to 115.7 meter elevation and the water table elevation is 117 meter. So from this we can find out H1 and H2. So H1 will be equal to 117 minus 114.6 and H2 will be equal to 117 minus 115.7. So H1 will be equal to 2.4 meter and H2 will be equal to 1.3 meter. Next, see this. It is given as 120 minutes. So TR is equal to 120 minutes. That is 2 hours. First, we have to find the specific capacity per unit well area of the aquifer. That is, we need to find Ks. Ks is equal to K0 upon A. That is the specific capacity divided by the area. So, K0 upon area. And the equation is 1 upon TR ln H1 upon H2. We'll substitute the values. So Ks will be equal to 1 upon TR. TR is 2 hours into ln H1 upon H2. So H1 is 2.4 meter divided by H2 is 1.3 meter. On solving, we get Ks equal to 0.3066 R inverse. Next question is, find the discharge in the well under a safe drawdown of 2.75 meter. For recuperation test, discharge is equal to 1 upon T or say 1 upon TR ln H1 upon H2 into area that is area of well into H. H is the drawdown. So this will be Ks. As you can see here that the equation for Ks is 1 upon Tr ln H1 upon H2. So discharge is equal to Ks into area of well into drawdown. So Ks is 0.3066 into area of well, that is pi by 4 d square, and d is 3. So pi by 4 into 3 square into drawdown. Drawdown is 2.75 meter. On solving this, we get discharge is equal to 5.96 meter cube per hour. Hence, the specific capacity per unit well area of the aquifer is 0.3066 R inverse, and the discharge in the well under a safe drawdown of 2.75 meter is 5.96 meter cube per hour.